Good evening, everybody, and welcome to AISC's Night School. This is Fundamentals of Earthquake Engineering for Building Structures, presented and written by Raphael Sabelli. Today is February 24th, 2014, and this is Session 1, Seismology in Earthquake Effects. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. Today's speaker is Raphael Sabelli, SE. Raphael is a Principal and Director of Seismic Design at Walter P. Moore. Raphael has earned a Special Achievement Award from AISC as well as a T.R. Higgins Lectureship Award. He is active in the development of seismic design standards for steel buildings and is a member of the AISC Seismic Provisions Committee, the ASCE 7 Seismic Task Committee, as well as the NIST Building Seismic Safety Council's Provisions Update Committee. Raphael also serves as the AISC Seismic Design Manual Committee Chair and was the project manager for the 5-volume SEOC, that'd be the SEA of California, their Seismic Design Manual. We're very pleased to have Raphael here as the author and lecturer for Night School 4, Fundamentals of Earthquake Engineering. Thanks for being here, Raphael, and I'll hand things over to you.
Thank you, Brent, and welcome everybody. I'm very happy to be able to spend the next 8 weeks with you, 8 to 10 weeks. I think we have a little bit of time off in the middle, and discuss a subject that's very close to my heart and my practice, which is earthquake engineering of structures, particularly steel building structures. This course we put together with AISC with some pretty broad objectives. We want to introduce the concept of earthquake engineering and hit the principles of this subject so that attendees will be able to understand what it is we're trying to do when we do design for earthquakes. Also, application of those principles in the basic procedures of seismic design, something that we'll cover from start to finish, and also how, in particular, how the material properties of structural steel are utilized in seismic design. So these are pretty broad objectives. They're not very detailed. In fact, in the course, we're not going to get into too much detail on specific seismic systems, but rather cover the principles from a general approach and get into the way that they affect our overall design procedures. Now, you have the handouts for this lecture, which are, of course, correspond perfectly with the slideshow that we're going to present. But I'd also like you to be aware of a number of other resources. For the course in general, I've identified 3 resources that you might consider having available. The first one is Earthquakes and Seismic Design. This is another AISC publication written by Ron Hamburger. It's part of the Facts for Steel Building series, and it's available as a free download from AISC.org. It covers more or less the same territory that we're covering in the 8-week seminar, addressing in general what earthquakes are, how we design for them, how we take advantage of the material properties of structural steel, and how that affects the design of particular systems. In much greater detail, we have the textbook Ductile Design of Steel Structures. This is the 2nd edition by Bruneau, Wang, and Sabelli. The 1st edition, also very good, Bruneau, Wang, and Whitaker. And it covers in great detail what the material properties are of structural steel and how we utilize those materials in the design of systems. And so if you want to go much deeper into those topics, that's a great resource. It is not available for free or for download. And then finally, the AISC Seismic Design Manual. This is a very extensive resource covering all types of systems in great detail, down to the calculations of weld sizes, number of bolts, dimensions of gusset plates, and the like. And so it's a tremendous resource for showing the application of seismic design. Obviously, it's an AISE publication, and there's a large group of us who spent a few years of volunteer time putting this manual together. It's cheap at any price, and I believe the member price is around $100 or so. In addition, for each session, at the end of the session, I've put a couple of other resources that you might consider if you want to go dig a little bit deeper into that particular topic, and this session is no exception. In addition to those books, there are a couple of other resources that I want you to be aware of. The AISE Seismic Design Manual Seminar, which is being offered live in cities across the United States. It was offered last year. It's being offered again this year. You can go to aisc.org/seminars to see the different locations and dates for that seminar. That seminar introduces the Seismic Design Manual and the seismic provisions. It covers in great detail the seismic provisions and how they apply to the design of structures. It also covers some misapplied provisions. So it's a very practically oriented seminar. Our intent with this course was not to repeat that material, but rather to present a more general treatment of seismic design. So we're going to focus on the principles and concepts, and this course can be thought of almost as a prerequisite for the Seismic Design Manual Seminar. It's going to lay the groundwork for application of these principles into specific design provisions for different structural steel systems. In addition to that seminar, we have the AISC Solution Center. That's a resource that AISC provides by phone, by email. I suppose you could write in as well. And they answer questions about structural steel design, about application of code provisions, the main specification, the seismic provisions, and the like. And it's a resource that you should be aware of. It's a great place to write in and get a good explanation of what a specific code provision is intended to cover, beyond what the commentary explains. So be aware of that resource. And then for this particular class, you can send in questions and comments and anything else you care to send in to nightschool@aisc.org. And as we go along, I'll be reviewing questions that are not addressed in the day's session, and we'll try to address some of those later on as we have time. So we're getting together for 8 sessions to talk about seismic design. This is the first session. We're going to cover seismology and earthquake effects. We're going to proceed from there to talking about the dynamics of structures, starting with single degree of freedom structures, then going on to multi-degree of freedom structures, a little bit closer to what we think of as buildings. Then we will cover steel behavior, and from there introduce the concept of system ductility as it affects seismic design. Then we'll cover braced frame and moment frame systems, building configuration, including diaphragms and load path. And then finally, we'll get into the system of building codes and some of the provisions that you need to be aware of. And with this, as all is preparation, it would be a great time after completing the course to sign up for the Seismic Design Manual Seminar. Okay, so session 1 covers seismology and earthquake effects. In this session, we'll talk a little bit about plate tectonics. We'll talk about earthquake energy being propagated as waves. We'll talk about how earthquakes are measured and how we refer to their size. We'll review some of the major earthquakes that have happened, especially in the last century, discuss earthquake effects, address some of the related hazards, and then discuss in very briefly but importantly the concepts of hazard, risk, and probability, which are fundamental to how we handle earthquake engineering. Let's start with plate tectonics. As you probably have heard many times, the crust of the Earth is broken up into several large tectonic plates, and these plates are in constant motion with respect to each other. Our configuration of continents didn't always look the way it does now, and it won't always look this way either. It has it is constantly changing as the plates slide past each other, under each other, and into each other. That type of motion carries a lot of energy with it. That energy is not released into the system all at once. Sometimes it's stored as strain energy and then suddenly released, and that sudden release of energy causes ground shaking or an earthquake. So this movement of plates has to do with it is believed has to do with movements in the Earth's mantle. Convection currents move the plates laterally. In some cases, the plates are moving away from each other. In some cases, they are moving under each other, and in some cases, they are simply sliding past each other. At each of these interfaces, there's the potential for strain energy to be built up and then released in the form of a violent earthquake. On the west coast of the United States, and you see the San Andreas Fault, we have the North American plate and the Pacific plate moving relative to each other, so that, say, San Francisco and Los Angeles might be moving closer together. That type of motion is a certain type of relative movement called a transform boundary. In the Northwest, we have a convergent type of boundary with a subduction zone where one plate is sliding underneath the other. And the characteristics of the ground motion are somewhat different at each of these, but still some of the characteristics are similar, and they both release a great deal of energy. There's also a divergent type of interface. We do not have that on the west coast. In Alaska, there's a long history of major earthquakes. That's another convergent boundary there. Plate movement. Along the San Andreas Fault Zone, we have somewhere on the order of 2 to 2.5 inches a year, depending on how many faults you consider to be part of that system. And at that rate, San Francisco and Los Angeles are about 15 million years apart. And so here's my little illustration of the difference, or the separation of San Francisco and Los Angeles, about 15 million years. Now, as the plates move past each other, they're at the center of the plate, you have probably a fairly uniform motion. But at the boundaries of the plate, there is strain energy that's built up. And here I'm showing it as a deformation of these squares into parallelograms. And the strain energy keeps building up as the plates try to slide past each other. And then at some point, there's a rupture, and there's an actual slip at that fault. And the release of that strain energy causes earthquake ground motion, which propagates as waves. So that's the mechanism that we're familiar with on the west coast of California, say the San Andreas Fault and parallel faults. We also can have strong ground motions, major earthquakes, in the New Madrid and Charleston areas, and these are not at plate boundaries. And to be frank, we don't know. There's no agreement on the mechanism, the underlying mechanism that causes these earthquakes. But we do know that these earthquakes have happened historically and that we do need to be prepared for them. So the New Madrid zone, Charleston, there's also an area in the Indian Ocean that exhibits strong seismicity without this plate mechanism. And we just don't know the source. It doesn't mean that we don't expect the earthquake. It just means we don't understand everything. So now let's look under the ground and see what's going on with seismic waves. Earthquakes can release strain energy in a very sudden fashion. That is going to cause high energy waves radiating from what's called the hypocenter underground. At the surface, these waves may change direction and radiate out from the epicenter, which is essentially where above the hypocenter on the surface. And these surface waves can be very high amplitude, and these are the waves that cause structural damage. So here's a very nice illustration of waves radiating out from the hypocenter. We have different types of waves, and you've probably heard some discussion of this. We have the primary wave, which is a pressure wave, and that radiates out in this sort of fashion with the Earth getting denser and less dense in radiating form, so pressure wave. There's also the secondary or shear wave that has a sort of shear deformation, and it propagates that way through the medium. Then when we get to the surface, we have Rayleigh waves, which kind of have a little bit of a pressure component to them. I'll do that again. And then we have Love waves, which are, again, more of a shear type of motion that propagates along the surface of the soil. Now, similar to waves in water, they will radiate out, and in general, the amplitude will gradually diminish as you get further and further from the source of excitation. So you'll get the highest amplitude at or near the center, and you'll get lower and lower amplitude as you go further and further out. So here's a nice graph of some measurements from different stations at different distances from the epicenter. And you also have, in these solid and dashed lines, you have numerical relationships, essentially models of how the energy attenuates or gets smaller as you get further and further out. So different seismologists have proposed different models for attenuation of ground motion. You can see that no model is 100% perfect, and you wouldn't expect it to be. There's a lot of variation that you see in the data. But we use these models to make predictions about the ground motion that might be expected at particular sites, based both on the intensity at the source and the distance from the source of that site. So this general decrease with distance or attenuation is a very important aspect of earthquake motion. So highest intensity near the source, lowest intensity away from the source. And here's a diagram of the New Madrid earthquake, historical. And you can see their intensities here given in Roman numerals. We'll talk about what these intensity measures mean in a few minutes. But for our purposes now, I just want to point out that the highest intensity is near the fault where the rupture is, and you get lower and lower intensities as you move further away. It's not a perfect circle by any means. It's a highly variable medium, and in some areas that medium can transmit energy at great distances, and in other areas that medium is not capable of transmitting the energy. Also, the source is not a single point, but might be a length of that fault. So you get a general relationship that the further you are away from the source of that motion, the rupture of the fault, the lower the intensity of the motion you're going to see. Now, the fault can rupture sequentially along its length. And there's an effect there that in the direction of propagation, you can get some accumulation of that motion. And sometimes when you're in a near source, this can result in a strong pulse type of motion. So where we are near a fault rupture, the characteristic of the ground motion may be a little bit different from when we're at a great distance, and there might be one strong pulse that carries a lot of energy and may cause a lot of structural damage. In addition to distance, the characteristics of the soil have quite a bit to do with the intensity of ground motion that's seen. This is showing records from the Loma Prieta earthquake. So you can see in this little inset, the epicenter of the earthquake is down here, essentially in Santa Cruz, and all of these stations are almost a couple of 100 miles away in Oakland. Even so, their relative distance from the source is all essentially the same, but the intensity of ground motion is very different. And the reason that it's very different is that the soil underneath is different. Here, perhaps in the Berkeley Hills, or Oakland Hills, we have a site on bedrock, very small amplitude of motion. At the opposite extreme, in the bay, on soft bay mud, we have very large amplitude of ground motion. And the reason is you can think of the soil as a spring. If you have some energy imposed on a spring, if it's a soft spring, you need large displacement to transmit that energy. If you have a very stiff spring, it's very little displacement. And that's that can help us understand why soft soils tend to have much greater seismic amplification than bedrock. Okay, this is a 3-component record of the Tohoku earthquake, so recent earthquake in Japan. You can see there's an east-west component, a north-south component, and an up-down component. And the vertical axes are the accelerations as a factor times g, the acceleration of gravity. So since we're dealing with an acceleration and a mass, you can compare this to, say, taking the building. At 1g would be taking the building and making it a cantilever laterally. Of course, this is a dynamic effect. It's not a static effect, but it gives you an idea of the level of motion that we're talking about. And I'll point out that we have strong acceleration in the east-west direction, strong acceleration in the north-south direction, and we even have strong acceleration in the up-down direction. We have a spike here that's almost 2 Gs. And that's something that we often ignore, but it can be an important thing for some types of structures. All right, let's talk a little bit about earthquake measures. I'm sure everyone's heard of Richter magnitude. That's a logarithmic scale, and so if you go up 1 unit of Richter magnitude, it's actually 32 times the energy. So if you go up 2 units, 32 times 32, that's almost 1,000 times the energy. It's fairly difficult to establish because the definition is based on standard instruments at standard distance, and we don't always have those. Also, we tend to lose some of the energy for the very large earthquakes. And so there are some issues with Richter magnitude. There's a similar measure called moment magnitude, also energy-based, and that is based on the surface area of a fault, the slip, and the rock modulus of rigidity. It gives results fairly similar to Richter. And then a completely different type of measure, modified Mercalli intensity. This is based on the effects. It is therefore, by definition, subjective. And it's based on conventional construction, as we'll see why that's a necessary assumption in a minute. There's some correlation between intensity and acceleration. The intensity scale is a 12-step scale. At intensity 1, the ground motion is not felt, except perhaps it's detectable by equipment, but people probably won't feel it unless they're extremely sensitive. At intensity 2, a few people, if they're in a still room, perhaps sitting down, they might detect it, or at the upper floors of building. Intensity 3, it definitely can be felt, but it might be mistaken for a passing truck. At 4, we're talking about a motion that definitely registers with people. It might wake people up. It might move some things around. At 5, it's already knocking things over. At 6, it might move around heavy furniture. It might cause some plaster to fail. And then we're getting into real damage. At 7, chimneys can fall down, although most well-designed buildings should be okay. At 8, we're starting to see damage to all buildings, including well-designed buildings. Here's a chimney falling over. That's typical earthquake damage in the 7 to 8 range. 9, we have considerable damage to all sorts of structures. We might see a few buildings with partial collapse, buildings falling off their foundations. 10, masonry buildings might have a lot of damage to masonry buildings. And 11, we're going to see a lot of devastation. Our heavier buildings, especially masonry, are not going to survive. And at 12, we have something that's called total devastation, and it can be hard to tell where the buildings were after intensity 12. So this gives you an idea of an intensity 9. There's a lot of rubble in the streets. We don't see any collapses here. And this is a historical earthquake from Lisbon, 1755. A cathedral fell down. A lot of buildings fell down. A lot of ships had trouble in the harbor, and that was considered to be, in retrospect, an intensity of 11. Also, intensity of 11 is Seward, Alaska. This is a 1964 earthquake, and a lot of buildings and tanks and other structures were knocked over, and it was very devastating for this community. As I said, intensity has some correlation to acceleration. So if we're talking about intensity of 10, we're probably talking about a peak ground acceleration of at least 0.6 Gs. So we can expect a lot of damage when we get to those high accelerations. And generally, we use the accelerations in design, although maybe not directly as this would suggest, but our designs are based on accelerations, and so you can imagine that we're trying to control damage at those large accelerations. However, for conventional construction, not necessarily designed for these high accelerations, we might see the level of damage indicated by this modified Mercalli intensity. Okay, there's also a rough correlation that can be drawn between the maximum modified Mercalli intensity of an earthquake and the magnitude of that earthquake. And this is taken from that Hamburger Steel Facts publication. So if we're dealing with an earthquake magnitude of 6 or so, we're probably looking at intensities of 7 to 9, and if we're dealing with magnitude 7 or higher earthquakes, we're dealing with some serious damage, intensity of 8 or higher. This is the Northridge earthquake with the modified Mercalli intensities graphed on there, and you can see in a few hot spots close to the source, presumably, and also perhaps on some bad soil, we have some intensities that rise to the level of 9, and then we have other regions around there where there are lower intensities. So just to make the point, this is a magnitude 6.7 earthquake. Intensity is useful in describing local effects. So at a particular site, in a particular neighborhood, we have this intensity. But magnitude is useful in describing the event as a whole, the total amount of energy released, and by implication, the amount of damage or the area affected. So you can have high local intensities, but that doesn't necessarily mean that the earthquake is a high magnitude. There's a rough correlation, but it's not perfect. Okay, so we have different areas that have historically had earthquakes, certainly a large number of them in California, but we've had them elsewhere in the West. We've had them in that New Madrid area, so the whole area of St. Louis, Memphis, population centers have significant earthquake risk. Charleston as well. And Alaska has had the largest earthquakes that have been seen in the United States, and Hawaii has had quite a bit in terms of both earthquake damage and tsunami. So we'll talk a little bit about some of the major earthquakes.
Raphael?
Yes.
Excuse me, before you move on to this next section, I do have one question I'd like you to address. The question is this: what is the connection between Richter scale magnitude in the IBC, which uses S sub S, S1, seismic design category, etc., but does not mention the actual Richter scale? And maybe a better question is, are we eventually going to cover this in later sessions, maybe?
So we will come as close as we come to drawing a line between Richter magnitude and the sort of ground motions that we design for later on in this session. But it's a good question, and probably the best answer is there's no real correlation between Richter magnitude and the ground motion that we design for, the accelerations that we design for. Instead, we use this sort of probability approach, as I'll describe at the end of this seminar. You can then figure out for your particular site an earthquake that your ground motion corresponds to, but that's not the process that we follow in getting our ground motions. So to answer the question, we don't go from the expected Richter magnitude directly to an acceleration that we design for. So you could say that there's no correlation. But when we get to the end of this session, we'll step back from that statement a little bit and show that there is actually, in some areas, where the ground motion that we design for does correspond to some estimates of what the magnitude of earthquake is, or at least what the a mechanism involving a fault rupture at a particular fault.
Okay, thank you.
All right, so we'll talk about major earthquakes. There are a lot of pretty small earthquakes. If we draw the line at magnitude 2.5 or less, there are almost 1 million a year. And as we look at larger and larger earthquakes, there are fewer and fewer. When we get to some fairly large earthquakes, where we expect, if they happen in populated areas, damage, so in the 6 to 7 range, there are about 100 a year. 7 to 7.9, these can be pretty devastating earthquakes. 20 a year, again, they don't always occur in populated areas. And then our very large earthquakes happen maybe every 5 to 10 years. These are the largest earthquakes that we have on record. Some of these are measured, some of these are quasi-conjectural, or at least estimated in retrospect as a function of damage. And I've made bold the top 3. The largest one was in Chile in 1960. The second largest one was in the United States in Alaska, magnitude 9.2. And I've also made, in this red color, all of the ones in the United States. And you can see that the United States earthquakes, well, they're all in Alaska. So on the West Coast, we like to think of ourselves as being the earthquake capital of the United States, but it just isn't true. We have larger earthquakes that have happened and can happen in Alaska. So these are all above magnitude 8.5, a lot of energy released. If you look at them as a sort of pyramid, you can see that those large earthquakes are very near the top, just a handful of earthquakes in that upper region of the spike, and then when we get down to magnitude 2 or so, we're talking about 1 million earthquakes a year, but these are generally not felt. If you look at the energy release, there's very little energy in that million earthquakes of magnitude 2. There's much greater energy in these just handful of magnitude 8.5 to 9 earthquakes. And you can see that in this graph. This graph is by area the energy released in major earthquakes. And you can see the top 3 earthquakes again here, Chile, Alaska, and Sumatra, roughly 50% of the energy released in a 100-year period. If you take all of the magnitude 8 to between the Sumatra earthquake and above magnitude 8 earthquakes, that's another 25% roughly. And the remaining quarter is all the other earthquakes put together. So these big earthquakes are huge in terms of the energy released. If you look at the 1906 earthquake, caused a lot of damage, magnitude 7.9, you can't even see it. It's just a sliver in this graph. So this Valdivia earthquake, magnitude 9.5, killed over 2,000 people, injured more than that, left over 2 million homeless, had a lot of property damage, and also triggered a number of tsunamis. 61 people died in Hawaii from the tsunami from this earthquake, and also $75 million worth of damage in Hawaii, $500,000 worth of damage elsewhere on the West Coast. 138 people killed in Japan, and $50 million of damage, quite a distance, and 32 dead or missing in the Philippines. The Earth's day shortened due to that earthquake, due to the change in the position of mass. Concepcion, a medium-sized city, moved about 10 feet, and the area of Chile may have expanded a couple of, maybe a square mile or so. And that just gives you an idea of how much energy is released. It has a global effect. We talked a little bit about cost with those earthquakes. Here are the costliest earthquakes. The recent earthquake and tsunami in Japan is probably the most expensive on record. However, 3 earthquakes in the United States are also up there in terms of the cost. Northridge earthquake, $20 billion. Loma Prieta and the San Francisco earthquake are also up there in terms of damage. The Northridge earthquake had $20 billion worth of losses, 60 people killed, a lot of people injured, over 20,000 homeless, over 40,000 buildings damaged. There were very high local intensities, perhaps 1.8 G. And finally, here we have the deadliest earthquakes. Fortunately, in the United States, we have not. None of the earthquakes that we've had have had this level of fatality. So far, we've been fortunate in that regard. I've highlighted here the recent earthquake in Haiti, where some 200,000 to 300,000 people have died. It was not one of the largest earthquakes, but with the vulnerability of construction, it had quite an effect in terms of death. And this is an interesting graph perhaps I won't dwell on it too much, but it shows you the year and the vertical axis, the magnitude in the horizontal axis, and the diameter indicates the number of fatalities. And there's not a strong correlation between the magnitude and the number of fatalities. A lot of it has to do with luck in terms of where the earthquake occurs near a population center, and a lot of it has to do with the quality of construction as well. The Haiti earthquake, magnitude 7, again, we're not quite sure how many people were killed, but it was in the hundreds of thousands. Many people injured. 1.3 million displaced, and Port-au-Prince was devastated. Over almost 100,000 houses destroyed or damaged, brings us up almost to 300,000. And the earthquake was felt very far away, Florida, Venezuela, and Colombia. Let's talk a little bit about earthquake effects. At the epicenter, we have perhaps the fault thrusting affecting the ground. We can have sliding and shearing the ground. There are some local effects of soil, and this is not necessarily at the epicenter, but may be in an area that's subject to liquefaction. There can be loss of support. There can be slope instability. So these are all local effects. Now there are widespread effects as well. There's horizontal shaking, there's vertical shaking, and this is what we design for. The local effects, well, if you're careful, you can avoid building on areas that might be subject to these effects, but the vertical and horizontal shaking you cannot escape without getting completely away from seismically active areas. This is a photograph of a vertical offset that occurred as a result of an earthquake. This is another one with an investigator there looking to see what happened. This is a horizontal offset that occurred, and of course you can keep your buildings away from these regions if you can properly detect them, but roadways and bridges often have to cross them. And again, a similar one. This is a recent earthquake in Haiti. So codes are going to keep us from building where we know there are these active fault ruptures. In general, we won't be allowed to build on those sites. This is a horizontal offset that occurred. I like this slide because it permits me to say manure pile a couple of times. But the farmer here was in the habit of shoveling out his barn and had a huge manure pile that would form under the window. As a result of the earthquake, the ground moved relative to the barn, and he didn't have to clear the manure pile. It moved on its own some 15 or 20 feet away. So I guess in that respect, the earthquake did him a service. Landslides can occur as a result of earthquakes. Either there can be unstable slopes, there can be lateral movement due to liquefaction. Liquefaction happens in saturated sandy soils as the vibration lets the sand move a little bit more like a fluid than it does normally. And so it's the analogy that's often given is that you could be standing on the sand at the beach and a wave comes in, and if you wiggle your feet a little bit, you can sink your feet down into the sand, and that's kind of what happens in an earthquake. So we get effectively a loss of strength for bearing when the earthquake occurs. The ground motion shakes the water-saturated sand, and the soil can flow laterally and vertically under the pressure. So here's a photograph of a famous case of liquefaction. Very rigid, very strong buildings. Nothing wrong with the buildings, but the underlying soil condition was subject to liquefaction, and so when the soil softened up under the earthquake, overturning moments couldn't be resisted in bearing in that soil, and the buildings simply flopped over. So codes are going to tell us we can't build on liquefiable sites or that we need to improve them. Here are a couple other effects of liquefaction. On the left, there's some lateral spreading that occurred due to liquefaction, and on the right, you can see classic sand boils where the liquefied sand acted like a fluid and simply bubbled up through the surface. This can lead to lateral spreading, and that can have a damaging effect, of course, on everything that's built on that slope. So we're not permitted to build over these known faults. However, there are many types of structures, roads and bridges, that have to have displacement capacity as they cross these faults. Soil subject to liquefaction or lateral spreading can be remediated, or we can use deep foundations to bypass these liquefiable layers. So these local effects we can get around. The shaking effects, ground motions, this is something we definitely have to design for. So there are horizontal forces, and here I'm showing an exaggerated effect on a building, but there are horizontal forces. Where there are horizontal forces on these on buildings, there is an overturning moment, and again, this is an exaggerated effect, but the horizontal force and the overturning are definitely things that we need to design for. So horizontal shaking, we design buildings to resist that horizontal shaking and the related overturning. The strategies for resisting that include providing adequate strength and stiffness, providing displacement capacity so the building can deform horizontally as the ground moves underneath it, and also energy absorption. Some of the earthquake energy can go into energy absorption rather than, say, inertial energy or kinetic energy. Related to earthquakes, we have a few other hazards. We have, of course, tsunami. That can be large movements of water caused by the earthquake, and that can affect areas that are very far away. The intensity or the size of the tsunami wave, of course, does attenuate the further you get, but still we're talking about large volumes of water. And in addition to that, there's a local effect as the tsunami moves up the shoreline, where the vertical amplitude of the tsunami wave gets magnified as the water moves inland. This is a recording of the 1960 tsunami in Hawaii, and this is one of the reasons that tsunamis can prove very deadly. You can see that there are several high peaks of tsunami wave, and they occur over the course of not just minutes, but perhaps hours. And you can see here there was a loss of data at some point. There may have been a large wave there. And so people sometimes mistakenly return to the shoreline, to their homes, when there's still more tsunami to come, and that can be a cause of loss of life. So when we have a motion on the ground floor that causes a disturbance in the water, that wave propagates and moves towards the coast. When it gets to the coast, there's an effect that the tsunami wave becomes very tall. That amount of displaced water aligns itself vertically, essentially, and can reach very high up on the shoreline. So currently, our codes do not address tsunamis. There are some public policy strategies about where to build. There are tsunami warning systems and in some areas refuges, but so far we do not build most of our structures to withstand tsunamis. Related hazards can include fires. This is a photograph of the 1906 of San Francisco in 1906, and you can see that there's extensive fire as a result, direct or indirect, of the earthquake. You can have so-called cascading events. There can be power loss that can affect critical equipment. It can certainly affect high-rise structures and make them very difficult to evacuate. You can have gas leaks and explosions as a result, disrupted transportation, and homelessness. Okay, before we reach the end here, I'm going to spend a few minutes talking about the concepts of hazard, risk, and probability. So hazard is a term that we use to correlate the probability of a ground motion to the intensity. So instead of talking about a magnitude 8 earthquake that we're designing for an earthquake with a certain return period. So the earthquake intensity for which we have a specific or a specified probability of exceedance. So probability of exceedance is another way of putting the same information as return period. Return period is kind of a useful concept, even if we don't use it all the time. But I think people understand at a fundamental level what it means to design for a 500-year wind as opposed to a 100-year wind. It's something that is a greater magnitude but happens less frequency, with lower frequency. And we have that approach when we talk about seismic design. We talk about higher return periods or lower return periods, or it can be higher or lower probabilities of exceedance. Now, there are two different ways that we get our ground motion accelerations for design. And there's the probabilistic approach and the deterministic approach. And if you've spent any time puzzling over the codes and how USGS creates these maps, you've heard about probabilistic and deterministic. And generally, people present this probabilistic approach and say that there's a deterministic cap. I don't think that's the best way to present the material. It describes perhaps the process that USGS follows, but it misses some of the meaning. I think the basic way in which we want to determine our ground motions is this deterministic approach. In the deterministic approach, which we might use, say, in San Francisco or Los Angeles, I say we, it means USGS might use this approach. We have a known seismic source, and we have an estimated magnitude that we're designing for. And that is perhaps a rupture of a certain length over the San Andreas Fault. You can say we're designing for a 7.9 earthquake at the San Andreas Fault, characterized by a certain rupture length. And then applied to that scenario, there are attenuation models that get us the acceleration that we might see at our site. We still have to consider the effects of soil, but we have the bedrock acceleration that's delivered to our site based on a certain rupture that, in this case, we could tie to a specific magnitude at a specific site. In that magnitude earthquake, though, that might, in that scenario, which segment of the fault ruptures, in what area, that might be a certain earthquake for a building in Berkeley, California, and it might be a different magnitude at a different segment of the fault for a building in San Jose. So we can't say that we're designing necessarily for a single magnitude of earthquake or a single scenario, but nevertheless, for each particular site, we may be able to tie the acceleration that we're designing for, if we're in the vicinity of a known site, a known source, we may be able to tie it to a particular scenario. So this is the way we like to design we like to establish our motions. We can say, for example, at a particular site, we're designing for a peak ground acceleration of 65% of gravity, resulting from an earthquake magnitude of 6.8 at the San Andreas Fault at 10 miles from our site. So that would be the deterministic approach. So USGS would establish that that magnitude was the likely magnitude, maximum magnitude in that area of the San Andreas Fault that would affect our site and therefore drives the acceleration that we design for. So there is a correlation between a magnitude and an acceleration on our site. It won't always be the same relationship, but there is a relationship. So we can do this in Berkeley, we can do this in San Francisco, we can do this in San Jose, I believe. We can do this all over Los Angeles, but there are a lot of areas where we simply don't know enough about the site. So where we are not close to one of these well-documented and understood sites, we have to do something else. And that's where the probabilistic approach comes in. In the probabilistic approach, we might have more than one source, including some very little understood sources. We still have to estimate the magnitude for these sources and their attenuation over distance, but we have much less certainty of what is going to dominate our earthquake risk. And we're going to do some work to correlate these intensity and return periods for different faults into a single intensity at a given return period. And this is something, well, I'll give you the type of statement that we can make. So at our site, we might be designing for a peak ground acceleration of 0.35 g, and that corresponds to a 2% probability of being exceeded in a 50-year period. Or you can also present that as a return period of 2,475 years. So this acceleration could happen at our site based on a fault rupture at any one of a number of nearby faults. And so it's a little bit less, it's less deterministic. It's a probabilistic approach. And this is the type of approach that we need to use where we're away from these well-understood faults. In different areas of the country, there's a different relationship between probability and or the return period and the acceleration. So if you look at San Francisco and Los Angeles, we have these sort of flat curves, and we have in this graph the annual frequency of exceedance, or you can think of that kind of as on this axis we have the return period. So return period of about 500 years, 1,000, 2,500. For a site in San Francisco, there is some difference in the intensity that we might expect for these different return periods, but it's not a dramatic difference. For a site in New York, there is quite a bit of difference between the 500-year earthquake and the 2,500-year earthquake. So we have to contend a little bit with that difference. When we talk about probability, we'll talk about a few different relationships that we can draw here. So P sub 1 is going to be our annual probability of exceedance. If we want the probability of non-exceedance, we simply subtract that from 1. So if you have a 2% probability of exceedance, you have a 98% probability of non-exceedance. Our return period has this relationship to the annual probability of exceedance. Then we can also construct the probability of exceedance for a period of years greater than 1, and we simply plug it in like that. Okay, so if we have the probability of non-exceedance in a 1-year period, and we multiply that, or we cube it, we multiply it by itself 3 times, that gives us the probability of non-exceedance in 3 years. If we simply multiply the probability of exceedance every year, that would be the probability of that level of ground motion being exceeded every year, and so that doesn't really make sense. So if you have, so do not multiply the probability of exceedance by itself, multiply the probability of non-exceedance by itself. All right, so if we want a period of 50 years, we put it in the equation like this. And then our probability of exceedance in 50 years is 1 minus the probability of non-exceedance in 50 years. So if we have a 10% probability of exceedance in a 50-year period, we can calculate the return period, and that's 475 years. Some people will call it 500 years, which is close enough. That corresponds to a 9.5% probability of exceedance in a 50-year period. Similarly, the 2% probability of exceedance corresponds to a return period of almost 2,500 years, fairly close to 2,500 years. Now, past codes have used both the 500-year and the 2,500-year return period ground motions. Our current code does it a little differently. Now, when we talk about multiple sources, it's a little bit complicated, but I think it's worth showing what we're doing when we're combining the effects of multiple sources. We want to maintain a certain probability of non-exceedance. And so what we're going to do is essentially solve for the magic acceleration x, such that when we multiply all of our probabilities of those accelerations together, we get the probability that we're asking for in the code. So here we have 3 different sources. If we want a 2% chance of non-exceedance, we want a 98%, if we want a 2% chance of exceedance, we want a 98% chance of non-exceedance. And so we're going to make sure that when we combine these 3 sources, the aggregate probability remains at 98%. And there's when you consider these sources, you have to cut it off at some point. Small and distant events have very low effect on the intensity. Here's a really nice pictorial graph of how we do this. This is from State of Oregon for a site in Portland. The different colors reflect different magnitudes. The different vertical axes essentially represent how much the event at that location might contribute to the probability of the acceleration at the site. So you can see for this site, some small magnitude events right underneath the site are affecting the design ground motion, but also some very large events away from the site are affecting it. And this is how you can get a single acceleration from multiple sites. So there is some logic to it. Don't worry too much if you don't understand it right away. You don't have to understand it, but at least you have some glimpse of what USGS is doing to give us these accelerations. And then if we have a small magnitude site pretty far away, it essentially has 0 probability of getting that high intensity ground motion, and therefore it doesn't contribute much. But the high intensity motion, even at a great distance, does contribute. Okay, so we're using the deterministic method to get our ground motion acceleration near major faults, probabilistic methods elsewhere. Probabilistic methods are probably not very relevant for our frequent events, say at the San Andreas earthquake. So we're considering shaking from multiple events, especially using the probabilistic method. We use attenuation models. The maps are created considering the seismicity as we understand it from significant earthquakes, historical intensities, and seismicity. Prehistoric geologic information where we detect that there was a major earthquake, and also satellite slip rate information can help tell us the strain rates at various sites. Based on all these things, USGS puts together this type of map where we get different accelerations at different regions. Of course, in the West Coast, you have to really drill down to see what the acceleration is, but elsewhere, maybe these types of rough maps can be used directly. In general, as an aside, the best way to get accelerations is from the USGS website. So the maps are periodically reviewed and updated based on new fault data, perhaps some new models for attenuation relationships, and perhaps also in fault rupture models, new satellite data, more seismic data. So every 3 years, USGS updates its maps and gives us the latest information to design for. Now, in our latest series of codes, we've changed from uniform hazard to uniform risk. Uniform hazard was a constant return period. No matter which site you designed on, you had the same return period. And that corresponded to this maximum considered earthquake with a 2,500-year return period in most areas except in the deterministic region. So you could say, given the maximum credible earthquake, we had a 10% chance of collapse. The latest ASCE 7 code uses uniform risk. So there's a risk-targeted maximum considered earthquake. Still, given that ground motion, if we've designed our building properly, there's no more than a 10% chance of collapse. But that ground motion is defined and selected such that if you design buildings properly for that ground motion and it occurs, there should be no more than a 1% chance or 1% chance of collapse due to earthquake in a 50-year period. So that is where risk comes in. So uniform hazard, same return period, uniform risk, same risk at each location, but different return periods to get to that uniform risk. And to do that, we need to make some assumptions of a standard fragility. So uniform hazard, again, we take the same return period no matter where we design for. Uniform risk, well, we're essentially integrating the area under the curve such that we can perhaps get a little benefit in New York for the fact that our ground motion doesn't carry much risk to it at lower return periods, but only carries risk to it at higher return periods. Okay. So a word about uncertainty. The maximum considered earthquake is essentially an arbitrary cutoff. There can always be a larger earthquake that we could consider, but this is societally what we think is an appropriate level to design for in terms of providing seismic safety and cost benefit. Larger events are possible, and earthquake demands introduce probably the greatest source of uncertainty compared to other loadings, except perhaps blast. So we're uncertain about the intensity, we're uncertain about the dynamic characteristics, and we might not even know all of the faults that could affect us. So in summary, we have tectonic plate movement causing releases of energy. That energy can be carried to far and wide as seismic waves, and they can affect our buildings such that we should design for it. We have ways of describing the event, including magnitude and intensity, to describe the effects of the event locally. Very large earthquakes are rare, but they represent a significant risk that we need to design for. And with that, I'll introduce my parting thought to get you thinking about what we'll talk about next week. How do our structures respond to these seismic waves? That's what we'll talk about next week. And now, before we get to questions, I will introduce The two additional resources that you might consider: Fundamental Concepts of Earthquake Engineering by Villaverde and the Seismic Design Handbook by Farzad Naim, both very good resources for understanding not just the material we covered today, but certainly the material that we covered today. And with that, we are at, 75 minutes and right at question time.
Okay, thank you, Raphael. We do have a few questions, and if everyone else out there has some questions, we will certainly type those in, and we'll address them as time allows here. First question here is, what is the basis for changing from the hazard to risk method that you just described?
Okay, what is the basis changing from hazard to risk? I believe this came through the Building Seismic Safety Council Provisions Update Committee, and the idea was that the cost to society of earthquake damage could be better described in terms of risk than in terms of uniform hazard. So, in other words, perhaps if we looked at the forces for a site in New York, that there would be relatively little additional risk in designing for a lower ground motion as compared to a site in Los Angeles. So we could essentially afford to design for a shorter return period for the site in New York compared to Los Angeles, and therefore we're taking advantage of it slightly in terms of this uniform risk approach. Now, we should be aware that we're not cutting our ground motions in half. In general, the changes are modest, from 0% to perhaps 15% at the outside.
Okay. Another question here. For the deterministic approach, how is magnitude/energy estimated for a given source?
So USGS has a number of models, essentially decision trees on whether segments of fault rupture on each fault, and so they don't start with a magnitude of earthquake. They start with a strain rate and a scenario of how much strain energy can be built up and how quickly can it be released, whether it's all released through several portions of a fault rupturing at the same time. And then they have attenuation models that they apply to that scenario to get the acceleration at different sites. Now, from that scenario, a certain number of segments of the San Andreas Fault rupturing, say in the Bay Area, they could also set by definition, there's an amount of energy released, and they can set a corresponding magnitude to that scenario. But they don't start with the magnitude and go to acceleration. They start with essentially the strain rate on the fault and a model of how much of the fault ruptures at the same time.
Okay. Next question. I would like to know how the probability of exceedance in X years and return period should or is related to building life expectancy. Should the return period be equal to the building lifespan for which one designs for it, or is there no correlation?
So often the probability of exceedance is given in a 50-year period because that's kind of what we understand the a reasonable lifespan for a building to be. But really, there's no direct correlation between that return period and the lifespan of a building. Now, if you wanted to invent your own approach for a temporary structure that will only be in place for, say, 1 year, for example, a construction crane, you could apply these concepts and figure out how much risk you could tolerate. But generally the building code doesn't like for people to do that. The building code assumes every building is essentially permanent, and the risk of collapse is the tolerable risk of collapse is uniform regardless of how long you think your building will be in place.
Okay, and then I guess along those lines, there's a question here about collapse. Is it specific to a certain type of construction, or is it always a possibility?
So we deal with this. Concept of collapse when we're talking about these high-intensity ground motions, and we generally don't see the level of collapse that we talk about in these major earthquakes. If you think of the recent earthquake in Chile, there were a few buildings that did collapse. By and large, though, there were not a lot of collapses. There was a lot of structural damage, a lot of buildings that could not be inhabited after the earthquake, but not that many collapses. In general, our new construction, even though we design we design using these concepts of a 10% chance of collapse given the maximum credible earthquake, we try to detail the buildings so that they have resistance over and above that level of collapse prevention. However, there is a lot of uncertainty in the ground motion that we're designing for, and so we certainly, as a profession, we don't want to overpromise what we're delivering. But in general, we don't expect widespread collapse of well-constructed new buildings. Some structures are perhaps less robust than others, but for those structures, we take added precaution. So a more brittle structure, as we will see next week, a more brittle structure we will design for a higher force than a more ductile structure, so that we can preserve a high level of reliability against collapse. So we do permit, even within seismically active areas, certain not so ductile types of construction, but we do things like design them for larger forces, apply significant height limits, and the like to make sure that they are not excessively vulnerable.
Okay, I'm going to move back to slide 97. The question is in regards to this, I guess, bullet point here, deterministic method used near major faults. And the question is this, what is considered near?
So this gets us from the difference between how I explained it and how it's actually done. The way that USGS does this, the rules that have been written in the building code for USGS to follow are as follows. The probabilistic method is used for every site. However, the deterministic method provides a cap, a maximum force So the probabilistic method could give you a, let's say you're designing somewhere in Los Angeles. The probabilistic method could give you an acceleration of 2.5 g, but the deterministic method gives you an acceleration of say 1.5 g, or perhaps 2 g, something lower than the probabilistic method. So you are, in that case, the deterministic method provides a cap, and that's what you use rather than the probabilistic method. So that makes it sound like there's some sort of upper bound to the probabilistic method, but that's not really true. The probabilistic method, though, has a lot of uncertainty to it, and it can give us some pretty extreme results where we're next to these very strong, or these faults that have a high slip rate and carry a lot of energy. And since we simply don't, some people will say that we don't believe those accelerations. Certainly we don't want to design for them. We trust the deterministic method because we understand the fault. That's what we use as an upper bound on the ground motion. So those are the practical steps that we employ in figuring out whether we use deterministic or probabilistic. Essentially, we use whichever is smaller. But for most of the country, deterministic isn't feasible. It's just we don't have that information about a local nearby fault.
Okay, let's try this question here. The person starts out with a comment that your explanation of the strong spring versus weak spring to explain how bedrock and mud affects an earthquake is excellent. Do you have such a example or explanation you could use to help grasp G-force or accelerations as it pertains to earthquake design?
All right, so I appreciate a challenge. Maybe I'll take that one home with me and try to come back with an answer in the coming weeks.
Okay, that sounds good. We can definitely follow up on that one. Here's a question: Does risk increase as time passes without an earthquake event?
Yeah. So the question is, is it a gambler's fallacy that we're due for an earthquake? And the answer is no. I'm sorry. Well, the answer to my question is no. The answer to the question posed is, in general, risk does increase. There's a lot of variability, however, but earthquakes do release strain energy, and strain energy has to build up. However, as you saw, the relationship between the energy released in a magnitude 5 and a magnitude 7.5, or magnitude 5 and a magnitude 7, you'd need close to 1,000 magnitude 5 earthquakes to relieve a magnitude 7. So if a fault is capable of producing a magnitude 7 earthquake, really only something on the order of a magnitude 7 earthquake is going to release enough energy to affect the strain, and to affect the strain energy that's built up. A magnitude 6 earthquake will not significantly reduce the likelihood of a magnitude 7 earthquake.
Okay. Here's a question: Can a large building affect the intensity on an adjacent building?
So the question, yes, in general, large buildings do affect, or the foundations of large buildings can affect the way the seismic waves are propagated locally. And that affects both the force as it's delivered to the large building, and perhaps in some adjacent areas as well. That phenomenon, I'm not going to say it's not well understood. I'll just say it's not well understood by me.
Okay. All right. Let's do one last question, and then we'll need to finish up here. And now, here's a question about, I apologize if I mispronounce this, spectral. I think he's trying to say dual spectral accelerations. Do these take into consideration all three types of waves that you described at the beginning?
So the spectral accelerations really they do take into account all the different types of waves, but it's the surface waves that really carry most of the energy to the structure, and so the response that we get from the response that we see when we do determine spectral accelerations, that response really is driven by the surface waves and not by the body waves. And we'll talk a little bit more about that next week. But the way that we get spectral acceleration is we have recorded ground motions, and we put those into a model where we have, say, a single degree of freedom oscillator, and we see how it responds. What is the acceleration that we get as we do a time history analysis with this ground motion and this oscillator, and we could try to separate out the recorded ground motion into the different waves, but really we throw them all in there. They're all in that record, and we get the response as a function of that record that contains all of the different types of waves.
All right. Thank you very much, Raphael. We do have a handful of questions we weren't able to get to, and we'll work with Mr. Sabelli and the AISC Solution Center as well to respond to those questions. But lots of good questions tonight. Thank you again, Raphael. Thank you, everyone that participated this evening.